Hello everyone and welcome to the University of Nottingham's live lecture. This lecture is brought to you from the Department of Mathematical Sciences and it's entitled Beyond Infinity. My name's Lisa Blake, I'll be your co-host for today. Before we start, I need to tell you a few things and then we'll start the lecture. First of all, this session is being recorded. You'll receive an email telling you where you can access this on our website when it's ready to view. You're all on mute, so if you have any questions at all, please post them in the question and answer session. And then after the talk, we will have time to answer questions verbally. You can type your questions throughout the lecture, and then I'll post them to the presenter at the end to answer. Captioning is available, so if you're having any problems at all with your sound, you can just pop the captions on. They're available in English and a number of other languages. So now I'd like to introduce Joel Feinstein, who is going to be giving a pre-recorded lecture and then will be joining us live for the question and answer session. Thank you, Joel.
Hello, I'm Joel Feinstein. I'm an associate professor in mathematics and I'm going to be telling you about infinity. We're going to be talking about a hotel with infinitely many rooms, and of course you can't really have one of those, but there's some genuine mathematics going on behind the scenes, and it's due to these two great mathematicians here, Georg Cantor and David Hilbert. Georg Cantor was the mathematician who discovered that there was really more than one kind of infinity, and David Hilbert had the idea of illustrating this by talking about a hotel with infinitely many rooms. Now most hotels have only got finitely many rooms. Here's a hotel with 5 rooms, numbered 1 to 5. And here come some guests. The hotel is starting to fill up. The hotel is now full, so if another guest turns up, they're not going to be very happy because there's no room for them. When every room is full, the hotel can't take any more guests. But Hilbert's Grand Hotel is different. It has infinitely many rooms, one for every positive whole number. But even so, sometimes every room has a guest in it. So the question is, what can the hotel manager, who's called Dave, do if another guest turns up? One day, when every room had a guest in it, one more guest turned up. No problem, said Dave. A minor inconvenience for each guest, that's all. So what did Dave do? You might want to think about that for a moment. Dave asked each guest to move one room to the right, as we see it, so that every guest added 1 to their room number. So the guest in room 7 moves to room 8, which is off screen. Then the guest in room 6 moves into room 7. The guest in room 5 moves into room 6. The guest in room 4 moves into room 5, and so on. The guest in room 1 moves into room 2. That leaves room for the new guest, who moves into room 1. A few days later, with all the rooms full as usual, a bus turned up which had infinitely many passengers on it. There was one passenger for every positive whole number. Their shirts were numbered 1, 2, 3, 4, and so on. Dave scratched his head for a bit and then said, "No problem, just another minor inconvenience for our guests." So what did Dave do this time? Again, you might want to stop and think about that for a bit. Dave asked each of the current guests to double their room number, which means that the guests in rooms 4, 5, 6, and 7 have to go off screen. The guest in room 3 moves to room 6. The guest in room 2 moves to room 4. The guest in room 1 moves to room 2. And that leaves all of the odd numbered rooms free so that the new guests can move in. Things started to get a bit harder for Dave now. Next week, the fractions turned up, a bus with infinitely many passengers, one for every positive fraction, with shirts labelled with the fractions in their lowest terms. So what did Dave do this time? Well, he had to think about it for quite a long time because there was a problem. He thought, well, I could fit in the guests 1, 2, 3, 4, 5 and so on, but then I've got all the guests like a half, a third, a quarter and so on. Well, I could probably fit those in as well, but then what about people like 2/3 and 3/4 and 5/8? Where are they going to go? Ah, I got it, he said. He started by asking everybody to double their room number, which freed up all the odd numbered rooms again. And then he said, right, if you've got a shirt which is labeled M over N, then you can stay in the room 3 to the power M times 5 to the power N. Now, why on earth does that work? Well, because of the way prime numbers work, these numbers are all different. If you change either M or N or both, 3 to the M, 5 to the N always changes. If you make M bigger, you can't compensate for that by making N smaller. And if you make M smaller, you can't compensate for that by making N bigger. You always end up with different numbers. So every guest gets a different room. This hotel is really incredibly popular. The next week, infinitely many buses turned up, and each of the buses had infinitely many passengers. Passenger N from the mth bus had a shirt labelled M, N. This time Dave didn't have to think. He said, I could do this exactly the same way I did the fractions. As before, he started by freeing up rooms 1, 3, 5, 7 and so on, and then he put passenger M, N in room 3 to the M times 5 to the N. But the next week, Dave finally had to admit defeat. The bus that turned up seemed harmless. It belonged to a firm called Cantor's. Of course, it had infinitely many passengers on it, but this time there was one passenger for every real number between 0 and 0.5. I'm sorry, said Dave. We can't fit you all in. You'll have to try the Hotel Continuum round the corner. To help with the next bit, let me tell you how each of the passengers was labelled. They each had a shirt which had the decimal expansion of their own number on it. But some numbers have got more than one decimal expansion possible. So when there was a choice, they always chose the one that ended in recurring zeros. For example, 0.4000 recurring is the same number as 0.3999 recurring, but the shirt they used was the one which was labelled 0.4000 recurring. So was Dave right? Was it really impossible to fit all of these guests into the hotel? We're going to prove that Dave was right using something called proof by contradiction. That means that we're going to assume towards a contradiction that Dave has found a way to fit all the guests in, and then we're going to make some deductions from that, which will lead us to a contradiction, and that will mean that there really was no way for Dave to fit all the guests in. So we start by assuming that Dave has managed to fit all the guests in, and then our next step is we define a sequence of numbers Bn. One for every positive whole number n. So B1, B2, B3, and so on. In fact, what we're trying to do is we're going to try to create a number of a guest who can't be in the hotel but should be. So these numbers Bn will all be either 3 or 4. And here's how we define them. If room n doesn't have a guest from Cantor's in it, we're going to set Bn equal to 3. Otherwise, room n does have a guest from Cantor's in, and then we do something different. In the case where there is a guest from Cantor's in room n, this is what we do. That guest will have a decimal expansion, 0.A1, A2, A3, A4, and so on, where those are decimal digits. And this is how we choose Bn. Bn we take to be 3 if the nth decimal place of that guest is not 3. So if AN is not 3, while if AN is 3, we take BN to be 4. So BN is either 3 or 4, and we don't have BN equal to AN. That's the key. So here we summarize the most important thing of the nth term of our sequence, which is that if a guest from Cantor's is in room N, then the decimal expansion does not have Bn in the nth place. So now we've got a sequence of 3s and 4s, namely B1, B2, B3, and so on. We use this sequence to make a new number called x. We set x to be 0.B1, B2, B3, and so on. Now that's a real number. Moreover, it's a real number strictly between 0 and 0.5 because these b's are either 3 or 4. Also, this expansion doesn't end in recurring 9s or recurring 0s because the b's are either 3s or 4s. And so this number x, which belongs to one of the Cantor's guests, namely guest x, is actually the correct expansion for guest x because it doesn't end in recurring 9s. Now, I'll remind you of a key feature of the sequence Bn that we chose, that for whatever positive whole number n you choose, if there's a guest from Cantor's in room n, then their decimal expansion doesn't have a Bn in the nth place. But we've got a problem with guest x. Guest x has got the decimal expansion 0.B1, B2, B3, and so on. And guest x is one of the Cantor's guests. So we've assumed they're all in the hotel. So guest x must be in one of the rooms. Say they're in room n. But then guest x from Cantor's is in room n and has a decimal expansion which does have Bn in the nth place, which contradicts what we said above. So starting from the assumption that all of the Cantor's guests are in the hotel, we've made logical deductions and arrived at a contradiction, which can only mean that it's actually impossible for all of the Cantor's guests to be in the hotel. So Dave was right. Now the hotel continuum is a bigger hotel. It has a room for every real number. But one day, even the hotel continuum couldn't cope. But that's another story.
Right, thank you very much. That was really interesting. We're now going to take some questions from the question and answers. Please do feel free to post any questions that you have that I can put to our presenter today. So we're going to start off with a rather broad question. If someone's thinking about applying to do mathematics at university, why should they choose Nottingham over perhaps different institutions? What are the benefits of coming to Nottingham for maths?
Well, we've got a wide range of staff who we have a wide range of interests and lots of expertise in lots of directions. Presumably, there's another talk that's specifically admissions directed that would have more information about this, given by Matthew Hubbard as well. So we've got all sorts of excellent features of our degree, but also good careers results and so on. Lots of people, employability and all that, and a lot of variation and choice inside the degree itself.
That's brilliant. Thank you very much. You touched on career options there. We have had another question about careers. What are the possible career paths after taking a maths degree? Again,
this is perhaps more of a question for our Director of Admissions, Matthew Hubbard, in his talk, but nevertheless, I can tell you that there's an incredible variety of careers available. So, I mean, maybe a lot of people go into the financial sector, banking, accountancy, and so on, but there's a reasonable number going to teaching, there's computing, and if you look at the different career paths that people have taken since they do this maths degree, it's just incredibly various.
Thank you very much. We have a question about the requirements to do maths at Nottingham. Is further maths required to be able to study mathematics here?
No, you don't have to take further mathematics, though you get there's more varieties, more ways of getting in if you do take further mathematics. So the idea is that we're looking for evidence of strength in mathematics beyond just an A in A-level maths. So yes, we expect you to get at least an A in A-level maths, but we want to see a bit more than that. One of the ways to demonstrate evidence of strength that's a bit more than an A in A-level maths is to get an A in some form of further maths, whether it's an AS level, not so common these days, or the A-level further maths. And if you do that, then you've met that bit. Otherwise, you might have to get an A star in maths if you're not taking any kind of further maths. Also, when it comes to the degree itself, if you do take further maths, then perhaps you've got a little bit more preparation for the degree. But if you don't take further maths, we don't assume it. We cover everything you need to know again. It just might mean you have to work a bit harder in first year, but then that can be a good thing.
Lovely, thank you very much. We have a question here. How can I improve my problem-solving skills? Do you have any tips for that?
Right, well, there's a lot of interesting web pages out there with mathematical problem-solving possibilities, things you can look at. There's the NRICH website, NRICH. If you look that up, you'll find there's a website there with lots and lots of practice problems you could look at on problem solving. And then there's all sorts of books you could look at. I'm just trying to think which are the best books to look at. I haven't got a recommended list in front of me. I used to like a book called What is Mathematics, which is quite good. There's something called Concepts of Modern Mathematics. But there are various other books available as well, which give you lots of practice in problem solving.
Thank you very much. For some of these questions, people can, if they wish, see our live talk on Mathematics Introduction and Overview, which is going to be taking place on the 9th of July, and we've posted some details in the Q&A section about that. Now, we have another question about the idea of uncountable infinity. When was this, well, discovered or thought of first?
Right, well, yes, it's, as I say, it was this mathematician Cantor who first discovered there was more than one kind of infinity. And I can't always remember the exact dates, but I guess he's late 19th century, early 20th century, I think. So it's that sort of time, along with Cantor was the one who discovered it all, and there was quite a big fight about it. In fact, there are some mathematicians who don't like to work with infinite sets at all, let alone countable or uncountable infinities. So there was a big fight, and a lot of people said that Cantor was talking nonsense because no one had ever seen anything like this before. But David Hilbert realized that Cantor got it right, and supported him. And people, well, at least, it's difficult to say whether maths is right or wrong when it gets that abstract, but that's the sort of modern accepted standard mathematics that most mathematicians work with, is now based on Cantor's ideas of sets and cardinality.
Lovely, thank you. We've had another question through about Hilbert. Yes. Since Hilbert, what work has been done and what breakthroughs, if any, have been made to do with infinity?
Right, now here's an interesting story, which is a bit sad about Cantor. You see, I've mentioned two different kinds of infinity in the talk. There's the usual countable infinities, which are the standard ones, which we've seen there's lots of different variants of, but basically the numbers 1, 2, 3, 4, and so on, the counting numbers, give you the countable infinity. And then I've mentioned an uncountable infinity, which is how many real numbers are there between 0 to 0.5, or how many real numbers overall, you know, there's uncountably many real numbers. But the question is there any size of infinity that's strictly between those two? Is there an infinity whose size is so that's too big to fit in the Hilbert's hotel, but actually still smaller than the size of the continuum, the number of real numbers. And Cantor spent a lot of time trying to determine the answer to this, kept thinking he got it, and it was probably driving him a bit crazy. But there was a very strange solution to this by a guy called Cohen, who finally cracked this, but he didn't crack it the way you'd expect. What he proved was Cantor could not have solved this problem because it is a problem that is known as independent. It's undecidable with the laws that Cantor was working with. You can't prove it true or false. In other words, you have to decide whether or it's one of these. It becomes a tenet of faith, whether or not you believe there's any infinity between those two. And some mathematicians take as an axiom and work with the axiom that there is nothing between those two infinities, and other mathematicians say no, we're going to work with a model of mathematics where I can't remember which I said. Some say there is, and some say there isn't anything in between, and neither of them can be proved right or wrong. Well, it's not quite that simple, but but that's basically the idea. It's a question that's independent of the usual axioms of set theory.
Thank you very much. We've got a question here which has had a large number of likes in our question and answer section. What set of numbers would be too great for the hotel continuum?
Okay. So rather than a set of numbers, the rule that goes on, suppose you've got, remember our initial hotel, which had 5 rooms and 5 guests turned up. One of the things you could look at if you've got 5 guests is you could say, okay, what are all the possible subsets of those 5 guests? You could take none of them, you could take all of them, or you could take some of them, but you might take these guests or those guests or whatever. Well, if you've got 5 guests, then the number of subsets of those guests is 2 to the power 5, which is 32. If you list all the possible ones you could have, I want to have guest 1, guest 3, guest 4, and so on, but not guest 5, not guest 2. You sort of look at the set of subsets, that's 2 to the power of the number of guests you started with. If you had just 1 room in your hotel, then it's 2 to the power 1. You've either got that guest or you haven't. So what it turns out is that whenever you've got a set, and you look at all the sets if you look at the set of possible subsets of that set, you've always got more. So the set of real numbers was bigger than the set of ordinary counting numbers. But if you look at the set of all subsets of the real numbers, like the set that's just got 1 e and pi in it, and the set that's got all of the counting numbers in it, or the set that's got all of the irrational numbers in it, or so on. Well, I mean, obviously, it's a really complicated collection of objects. Well, if you've got 1 guest for each of those, every possible subset of the real numbers, that's too many for the hotel continuum.
Thank you very much. I have someone, this question may be better to ask perhaps in the mathematics introduction and overview, but I've got a question from someone who's hopefully going to be studying physics, but is really interested in this sort of maths and wonders if there's any math societies that maybe they would be able to join.
Math societies, there is a math society, yes, it's MathSoc, and they're fairly active, and so I don't see any reason why someone who's doing physics shouldn't join MathSoc. That sounds fine to me.
We have another question about the concept of infinity and about how it's linked to applied maths. Have the concepts of infinity been used in any applied maths, and could you give us a brief overview? Okay,
well, generally applications of pure mathematics and applied mathematics, there's loads. It's not the sort of thing that I usually do myself, but sometimes an applied mathematician from down the corridor will come and knock at my door and say, okay, I'm trying to answer the following question, which is an applied maths question, but I need to know whether this situation is always valid or whether there are some exceptions. And then I will sort of look at it from a pure math point of view and say things like, well, this will work if your function is continuous, but not if your function has got jumps, or it'll work as long as your function is smooth enough, or something like that. So the sort of the theory of functions is the most common feature of how a pure mathematician helps the applied mathematicians. There's also a lot of stuff about complex numbers and so on. So the notion of infinity, where does that come in? I don't think that countable and uncountable come in very much when you're dealing with applied mathematics, but you do often have to deal with some very big sets, like sets of functions. If you're doing quantum mechanics, then you're quite often dealing with, because, not that I'm an expert on quantum mechanics, but because quantum mechanics is not so much about where is something exactly, but what's the probability that it's over there. All these things have got their wave functions and so on. And these functions really tend to live in what, interestingly enough, something called a Hilbert space, because Hilbert did a lot of different things. And one of the things he did was look at spaces of functions with interesting properties, and they were really important. But it turns out that these Hilbert spaces were really key when it came to studying quantum mechanics. So that's one of the applications of sort of infinite sets. But you know, the pure mathematics turns up all over the place. Linear algebra, theory of vectors and stuff, but in high dimensions, turn up all the time when you're doing applied mathematics. So I'm not going to be able to list all this, but I did. I think I'm trying to remember. I think I've got a blog post about it somewhere on my blog.
Thank you very much. That's really interesting. We've got a question here. Is there a cap to the types of infinities that you can have? This person has sort of expanded on this idea. They've said, presumably you can invent more sets of bus passengers too big to fit into uncountable infinity, and then have type 3 infinity, type 4 infinity, and so on.
It doesn't stop. There is no biggest infinity. There is something called Russell's paradox, which is that you see, you might think, I'll just take the set of all sets, and that's it, and that's the biggest possible infinity. But actually, there isn't a set of all sets. That isn't a set. Russell proved that with something called Russell's paradox, which I won't go into right here. So the point is, so it's the other thing. If you take what you think is your biggest possible set, you say, oops, let's look at the set of subsets of that, and that's bigger. So there is no biggest infinite set, because if you look at the set of subsets of it, that's even bigger, and that always happens. So yes, you've got type, you can describe, though it's not exactly clear what they are, but yes, you can talk about type 1 infinities and type 2 infinities and so on, but it keeps going. And even if you then you get to, you can think of your type infinity, but then you can get bigger than that, and so on. It goes, you go through all the different kinds of infinity as well, and you never get to a biggest one.
Thank you very much. Slightly more relevant question to this actual studying mathematics. Do you have any tips for exam techniques pertaining to mathematics in particular, and how people can work on their exam techniques and practice?
Okay, well, so of course that may depend on what sort of exam you've got, which will depend perhaps on what's going on in the world at the time. So at the moment, some of our exams are take-home exams, whereas our usual exams would be sit in the lecture room, sit in a big room with lots of people and take a live exam. So that sort of, there's a variation in the kind of exams that you take. So if you're doing a timed exam, well, I'm not an expert on exam technique, but one of the things that can happen to you in an exam is you might panic. And if you panic, that's okay. You can allow yourself a little bit of time for panic, but then you just need to calm down, because you've still got time to solve that and get back to things. So one of the things you can do in preparing for exams is learn about exam stress and how to handle it, because that's actually a surprisingly relevant thing. Now, assuming that you are able to handle your exam stress and it doesn't stop you from answering your questions, then it's a good idea to actually read through the questions before you start actually doing anything, so that you know which questions you actually are pretty much able to do. If you've got a choice of questions, and again, that varies from exam to exam. Sometimes you've got a choice of questions, you may find it's not a good idea to start a question where you definitely can't do the second half, or you think you probably won't be able to do the second half, when whole questions are better. On the other hand, if you've got no choice in the questions, then a quick look through to give yourself a feel for what's coming up is still a good idea. But since you've got to answer all the questions anyway, then you can have a go at that. You can just get started. The one thing I once did in an exam, which was really terrible, was I got much too interested in one of the questions and I refused to leave it even though it was hard. I remember that I spent most of the exam on that one question because I wouldn't let it go. And then I realized how little time I had left and answered as much as possible in the remaining time. This is not probably the best way to do an exam. So yes, time management's important. And if you shouldn't spend much more time on a tiny part of an exam question than it's worth. So you don't want to spend, if it's a three mark part of a big question, you find you're spending half an hour on it, that's probably not the best use of your time. You can always come back to it later if you finish the other stuff.
Thank you very much. Some wonderful tips and a lovely story there. We've got a question going back to what you said about sometimes the logic becomes so abstract that it's hard to tell whether what you've done is right. This person's asked, how do you know that if a proof you've done is right, if you can't kind of visualize it, and if the logic is so abstract, how can you actually prove that it's true?
Well, this is where peer review comes in, because it is easy to fool yourself, especially if you're absolutely sure something is true. Now, you see, there was an attempt to formalize mathematics. Russell and Whitehead again. The question was, could you just list a set of axioms and deduce everything that was true from them, and not accept anything that wasn't in a not accept any argument that wasn't in a a strict form that started from the axioms, made deductions in a sort of computer-like way, and arrived at certain results. And people wondering whether that was whether that would work. And then Gödel came along and showed that there was a problem, that whatever axiomatic system you set up in the first place, as long as it had algebra and numbers in it, then there was guaranteed to be a statement about numbers that you could state that would be true but not provable in your system. Or you've taken too many rules and your system has got a contradiction in it. And neither of those are very pleasant, and that upset a lot of people. But that means that the complete pure axiomatic approach, there's a problem at the basis of mathematics. There's guaranteed to be something missing. So all you can do is choose what set of rules you are going to work with, and then which set of arguments you're going to accept, and do the best you can. And occasionally these things turn up that are undecidable, like the problem Cantor was working on. But pure mathematics is still perhaps as close as you can get to certainty. I was quite a fan of the certainty you got from pure mathematics, and it upset me a bit when I discovered that even pure mathematics had problems at the foundations. But it's still, it's not like a physical theory, a theory of physics, where it's working so far the model for the universe, but then some phenomenon turns up that doesn't fit, and then you've got to find a variant of your theory to make it work. The things, what pure mathematicians can be absolutely sure of is that if you make some assumptions, certain things do follow from those assumptions, and that much is absolutely sure. But even there, the question is relevant, because when people write a mathematical paper, they don't go back to foundations. they start from recognized other recognized facts in the literature and results that have already been proven, and work from there. And moreover, people don't always include all of the details of their arguments, because it would expand their paper from being 10 pages to being 1,000 pages if they put in every little detail. So they say they take certain steps as obvious, which are also obvious to anybody else who's working in that area. But occasionally people make mistakes and say, think that things are obvious, don't include that detail, say it follows easily that, and occasionally someone finds a mistake. It's quite rare, because fortunately, because most people, when they say, most of these mathematicians are pretty good, and the peer reviewers are good, and if there is a gap, it'll be found. But occasionally someone says, this follows easily, and it isn't actually true. So can you ever be absolutely sure that your proof is right? Perhaps not. But if it's been around for hundreds of years, people have been studying it and using it for 100 years, and it's a famous theorem, then I would say it's almost certainly right.
Thank you very much. We've got a question here. Well, infinity is quite a sort of ungraspable concept to a lot of people, a little bit slippery. Why do mathematicians use it? And I guess you could turn this on its head and say, what would happen if we didn't use infinity as a concept? Well,
so the first, I mean, what are you going to do about the fact that you got all these numbers 1, 2, 3, 4 in the first place? That I have seen, I think, around in the world, people saying that actually there is a biggest number, you know, but obviously I would say, you think you've got your biggest number, well, I'm going to add 1 to it. I don't think they're the biggest number myself. So it seems a pretty natural concept. There do appear to be infinitely many different counting numbers. There doesn't seem to be a biggest one, because you just add 1 to it, whatever you think is your biggest one, and you've had it, right? So it seems even there, and that, as we know, is a relatively small kind of infinity, there do seem to be infinitely many already. And if just even working with numbers, which are some of the most natural things that we deal with, you're dealing with infinitely many things, then it seems to me that you're likely to have to deal with the concept of infinity somewhere along the way.
Lovely, thank you very much. A question here from someone who's interested in mathematical computation, and he's asking if it might be better to take a maths degree or a computer science degree.
Right. You might even be able to take both. In some places you could do maths and computer science, or sometimes data science or things like that, or you can do that at a master's as well. There's various options in various places, but if you do a maths degree here, then you can take some computer science modules as optional modules as part of your maths degree. Once you get to second year, you can take about 1/6 of the year could be taken in other subjects such as computer science. And if you're doing a computer science degree, actually they teach you some maths that you need for computer science as part of the computer science degree anyway, but you might be able to do some maths outside as well. It depends. I'm just trying to remember which of our maths modules would be suitable. That's less common that way around, I think, because I think what happens in computer science is that they teach you the maths that you need to know for computer science, and most of the maths modules in our department, what we call the honours maths modules at least, tend to depend on each other, and you need the suitable mathematical background. But there are some modules that students from outside maths can take, just it's a different set of modules.
Lovely, thank you very much. We've got a couple of questions asking about the Navier-Stokes equations and how they relate to infinity. Could you give us a brief introduction to what that is?
I'm afraid I'm not an expert on the Navier-Stokes equations. I'm not going to be able to help you there. So you move it, in general, when you move into the theory of differential equations or partial differential equations, or and so on, you can get to these incredibly complex. I mean, once you get to physics, fluid dynamics, applied mathematics, the systems of equations you're trying to solve get incredibly complicated, and can be unstable, as we've seen with the weather. They are, you know, they try and make a weather forecast, and they've got really good data as to what's going on at the moment with the weather, and yet they cannot accurately tell you whether it's going to rain where you are in the next half hour or not. They can try, but they can't be sure. So once you get to complicated systems, you're going to probably have to do some sort of approximations and convert things, and maybe computer modeling. Maybe sometimes you can make simplifications and get really good approximations, and sometimes you can actually get some proper theoretical solutions to some of these problems, but I can't tell you much about the linguistics.
Thank you very much. What kind of skills does a mathematician need?
So, well, of course, it depends on the kind of mathematician, but and of course, the first thing you think of is numeracy. But I mean, the numeracy, you get that at A level already, right? Or even before, and being able to work with numbers and do that sort of thing. That is, of course, important when you're doing mathematics, but it's very basic and a sort of low level part of it. So the numeracy is there. If you've got a math degree, obviously you're very numerate, but then there is mathematical reasoning and logical thinking, particularly in pure mathematics, but also important in applied mathematics, because, well, if you can't reason logically, you're going to make all sorts of invalid assumptions and claim things that don't necessarily follow. In pure mathematics, this is absolutely key. In applied mathematics, you still don't want to be making wild assumptions that aren't right. And then there's problem solving. Again, when I think of problem solving, I normally think of problem solving in pure mathematics, but there are links, and there's plenty of problems to solve in applied mathematics as well. And problem solving, of course, is relevant to the real world. So when you get your job in the real world, you're not expecting, well, it depends on how routine a job you get, but assuming you're getting a job where you might be faced with something where you haven't done exactly that before, you might have to think about what you're doing. And if you've never solved a problem before, if you've never been faced with a problem you didn't know how to solve before, and then thought about how you might solve it, and then worked on it, and worked to solve it, then that, you know, in the maths degree, this is the sort of thing you're going to do. You're going to have to learn to solve problems that aren't completely routine. When you're doing A-level mathematics, to some extent, you can drill. You can look at questions and say, this is a question of a type, I've seen 10 of this type before, and I can do this the same way I did the others. I've learned how to do it. And to some extent, you can do that in a maths degree as well. You can learn some routine things and do those and get practice and be really fast. Of course, when you come into an exam, the more routine stuff you can do, the more time you've the more time you've got to think about the things that aren't routine. So as a mathematician, you really need to be able to deal with things that are not routine and solve problems. But of course, the better you are at routine stuff, the more time and energy you've got to deal with the stuff that isn't routine.
That's lovely. Thank you very much. And we are going to have to end this question and answer session there, as we've just run out of time. However, I would like to thank Joel for his really enlightening lecture, absolutely superb, and some wonderful questions coming in there as well. Here are some useful links, so if you've got any further questions, you can use these links to contact us. As I said, we do have our mathematics introduction and overview talk on the 9th of July, which will also be recorded and on our website afterwards. So please do contact us if you've got further questions. So thank you to Joel Feinstein for his lecture, and I'd like to thank all of you for attending and participating in the question and answer session. Thank you very much.